So it looks like we're doing hyperbolic functions.
Yeah.
All right. These can be a little tricky. So let's kind of start from the beginning. What's the most elementary hyperbolic function?
Isn't it 1 over x?
What's the vertical asymptote?
Which be 0?
X equals 0. What's the horizontal asymptote?
This is what I'm confused on. Is it 0
Yes.
or not?
It's y equals 0. Now, here's the rule. As long as the bottom has a higher degree than the top, in other words, if I had something like this, it doesn't matter what else follows the x cubed. The only thing you care about is the highest degree polynomial in the numerator and the denominator. If the denominator is bigger, then it's always y equals 0 is your horizontal asymptote.
All right.
Okay? The other situation, there's only 3 situations. That's one of them, where the denominator is bigger. The other is where the denominator is the same. Same size. What's the horizontal asymptote on this function?
Is it 1?
It's 2/3. It's the ratio of the coefficients.
Okay.
Only because it's x squared there and x squared there, or if it was x to the 5th and x to the 5th. It's all you care about is if they're the same degree, then the horizontal asymptote is the ratio of the coefficients. That's situation number 2. There's only one other situation that you're going to have to worry about, and that is problem number 26, where the top is exactly 1 bigger than the bottom. When this is the case, you almost always have a vertical asymptote somewhere. And in order to figure out what other asymptotes you have to divide that manually. Okay? You're going to have a oblique asymptote. Whenever the top is exactly 1 degree higher than the bottom, after you do this division, you're going to have a linear function. That's going to be this dotted line right there. So first of all, let's do this division. Because the only part of it we really care about is the part, the linear function. Now remember, we have to allow for a x term when we're doing this, like this. You see what I did there?
Yeah.
Okay. Let me do this. What goes here?
Is
it only thing you do is you take that term and you divide it into that term. And that's what goes there.
So 2x.
2x. Now you take that 2x and you multiply it by both terms. In other words, we're doing long division just like we normally would. So that becomes 2x squared plus 4x, subtract like we normally would, and repeat. In other words, now divide that into that, and you get minus 4. Okay? Multiply the minus 4 by both terms. Subtract, you get a remainder of 5. So this is a remainder of 5 divided by x plus 2. You with me?
Yeah.
The only thing we really care about is this linear term right here. That is the equation of the oblique asymptote.
Okay.
2x minus 4. So, here's what we have on this problem. Where's our vertical asymptote? On number 26.
-2.
Okay. The equation of our oblique asymptote is y equals 2x minus 4. Goes through a y-intercept of 4, has a slope of positive 2. Let's make it look like this. And that goes all the way down. In other words, it crosses the vertical asymptote. So this is what your basic framework looks like. The key whenever you're graphing hyperbolic functions is to lay out your vertical, your horizontal, and your oblique asymptotes. Once you get those laid out, you kind of know what the curve's going to look like after that. All right? It's going to have one of 3 shapes. And unfortunately, here, let me redraw it because I've drawn this way too large. I'm going to put -2 right there. And I'm going to put 4 right there. And I'm going to have a slope of 2. So this is my basic framework. Now, I know that because it's hyperbolic in nature, it's going to look either like this. You with me?
Yeah.
Or it's going to be in the other 2 quadrants. In other words, it might be like this. This kind of hyperbola. It's in this quadrant and this quadrant. Whoops. On the bottom end, it's always got to be approaching the asymptotes. Okay? So it's possible that it could be in what you might call the 2nd and the 4th quadrant, or the 1st and the 3rd. Okay? To determine which one, let's test a point. If I let x equal 0, what does y equal?
So I plug in the entire equation.
Just plug in x equals 0. What do you get for y?
-3/2.
Okay, so when I'm at x equals 0, I've got to be in this quadrant right here because I got to be -3/2. So, in other words, I'm going to be in quadrants 1 and 3. I'm not going to be in quadrants 2 and 4. My hyperbolic function is going to look something like this. And then on the other end, it's going to be there. Okay? Now, as to exactly what that point is, that's awfully hard to determine without a calculator or calculus. If you knew calculus, we could determine it. Or if you had graphed this on a calculator, we could determine it. Figuring out what it is on the graph that we're going to graph manually, extremely difficult. I don't even know how to do it. Okay? However, if I graph this function, this is what Wolfram alpha gives me. Okay? Let's look at it a little more closely. It's the same thing as what I drew. It's in this quadrant and this quadrant. It doesn't have exactly the same shape because my scale was off a little bit. but I can tell there's a vertical asymptote right there at -2, and there's an oblique asymptote. If you look at the zoomed out version here, we can see that there's a slanted line that represents the oblique asymptote. And it's only because of their scale that that doesn't look like it's a slope of 2. Notice their horizontal scale goes 10, 20, their vertical scale goes 50, 100, 150. So it's not the same scale vertically and horizontally, but it does have a slope of 2, that line. Okay?
Okay. Yeah.
All right, let's go on. Because that's really the hardest one of the bunch, to be honest. Let's look at 27. Is there a vertical asymptote on 27?
Yeah.
What value of x makes the denominator 0? There isn't any.
There isn't? Okay.
No, in other words, x squared is always positive, and when you add 8 to a positive number, you always get a positive number. So the denominator is never 0, meaning there's no vertical asymptote. X can take on whatever value we want.
Okay.
Is y going to be positive or negative? If the denominator is always positive, then y is always negative, because the numerator is -24. What's the horizontal asymptote? Y equal 0, because the denominator has a higher degree than the numerator. The numerator doesn't even have an x. Even if it had an x, it would be y equals 0, because the denominator would have a higher degree. It's x squared. So we know that the one value that y can never attain is 0. Notice that if we take -24 and we divide it by a positive number, we're never going to find 0. However, as x goes to positive infinity, y heads towards 0. So we have something that's going to look kind of like that. In other words, y is always negative, but as x gets really big, it's going to go to 0. Y is. And as x gets really negative in the negative infinity, it's going to head towards that. Well, what's it equal to when x equals 0?
-3.
Right there.
-3.
This curve should look something like that. There are no vertical asymptotes. There's a horizontal asymptote. Y is always negative. And it's symmetrical about the y-axis. It is a even function. Okay, let's just plug this one into Wolfram alpha, -24 over x squared plus 8. -24 divided by the quantity x squared plus 8. Notice that they got something very similar to what I drew.
Right.
Okay? The whole name of the game here is to figure out your asymptotes and then go from there. Okay? It's always the first step. So, what's the vertical asymptote here? If there is one. On 28.
Yeah, I know. My teacher keeps telling us to put it equal to 0, the denominator
Well,
equal to 0.
let's do it. X squared plus 3 equals 0. Is there a solution for that?
No.
In other words, again, we have the denominator always positive. It's never 0. There's no way to make it 0. There's no value of x that makes it 0. So we don't have a vertical asymptote. How about the horizontal asymptote? The degree of the variables are the same. So the horizontal asymptote is what?
1.
Good. Again, what's y when x equals 0?
-4/3.
Okay, let's make that point right there, minus 4/3. And so we know the function goes through that, and we know that it's asymptotic. Whoops, I drew it wrong. Hold on. It's asymptotic to that asymptote. And again, on the left side, it's the same thing. In other words, it doesn't matter whether x is positive or negative, y is the same. Again, it's an even function. So as x goes to negative infinity, we're going to approach the horizontal asymptote. That's the definition of an asymptote, of a horizontal asymptote, is what y approaches as x goes to either positive or negative infinity. All right. Let's look at 29. Let's get through some ones that aren't all the same. Okay, 29, vertical asymptote.
It would just be 1.
Well, let's solve this equation. Like your teacher said, let's make it equal to 0, which means x squared equals 1, which means x equals what? When you take the square root of a function, of an equation, what's the first things that should be out of your mouth?
Plus or minus 1.
There you go. Notice that when x is minus 1, the denominator is 0. When x is plus 1, the denominator is 0. So I've got a vertical asymptote at 1. I have a vertical asymptote at negative 1. What's my horizontal asymptote on 29?
Zero.
Correct. Because the bottom is greater degree than the top. Horizontal asymptote's always going to be 0. Now, when you have this kind of a grid, where you don't have 4 quadrants, you have 6, basically. I got 3 on top and 3 on bottom. Well, generally, the curve's going to look something like this. In other words, it's still hyperbolic in nature. Comes up from negative infinity, usually goes through some point on the x-axis, and then comes up on the other side like that. Okay? Sometimes this middle part won't cross the x-axis, and it'll just do something like this. And then sometimes the part on the left will come out up top like that. So what do we have to do? We have to plot a few points, right? To see where we're at over here. Well, what point should we put in for x to see where we're at right here? Whether we're here or here.
Positive 2.
Okay, what happens when you plug in positive 2 for x?
It's 9 9/3, so 3.
Okay, so when x is 2, y is 3. That means we're in that quadrant right there. So our curve's going to start out like that. Okay? Just for the heck of it, let's find out where we're at to the left of this vertical asymptote. Before we tackle what's going on in the middle, let's figure out what's going on to the left. Plug in minus 2 for x.
Yeah.
Okay? That's down here. Okay? Minus 2 1/3. Well, that's 0. So minus 2 1/3 would be somewhere here. That tells us that that's what it looks like on that end of it. Now, let's see if we can figure out what's going on in the middle. First of all, the thing that would be kind of nice to know is, does this thing cross the x-axis? How can we determine that? In other words, we got two choices at this point. Either it's going to do something like that, or it's going to do something and cross the x-axis and go on up. That's the only two ways I've ever seen it. And I've never seen anything different than that. So, to determine which, let's see if there is an x-intercept. How do we do that? What would y have to be?
0.
Okay, so let's take this equation, set y equal to 0, and see if we can solve it. If we can find a value for x that makes y 0, then it does indeed have an x-intercept. Well, for this function to be 0, what has to be 0? The numerator.
Yeah.
In other words, the first step in solving this would be to multiply both sides by x squared minus 1, which means this has to be true. But it's a good shortcut to know that if something is equal to 0 and it's equal to a rational function, then that rational function's numerator has to be 0. That's the only way that y could be 0. Well, does this have a solution? Indeed it does. If x is equal to minus 1/4, y is equal to 0. So, I go over here, I go to minus 1/4, I know that the function goes through that point right there. Okay?
All right.
One way I heard one teacher talk about this was that if you start from the right, okay, you go into this vertical asymptote at plus infinity, on the other side of that vertical asymptote, you're going to come out at minus infinity. So I know the first part of that curve looks like this. I'm going to cross the x-axis where I thought it was, and then I'm going to go up to there. So there's my curve.
All right.
Only other point that might be interesting is what's the y-intercept? What is it? How do you get the y-intercept from this function?
Put x as 0.
So what do you get when you do that?
-1.
All right, so I picked it pretty good, -1 right there. That's where it crosses the y-axis. This is where it crosses the x-axis. And the general shape is generally going to look like this. Once you've spotted the first quadrant, working from right to left. Okay? If I were to stick a negative sign in the numerator, then it changes the whole shape of this curve. It probably makes this thing down here. It makes this thing not there, but up here. And it probably makes this thing do something like this instead. Okay? So, in other words, it's possible that we're not always going to be in the first and third quadrant with the two ends of our hyperbola. We might be in the second and fourth. And you have to figure that out by just plugging in a point. All right, let's look at this one, 30. How do we get the vertical asymptote?
Plug or put it to 0.
Solve that. Which means factor it.
Yeah. It's -5 positive, or it's 5 and 1, but
Okay, first of all, the two numbers have to multiply to 4.
oh no, it's 4 and 1.
And what are the signs?
Both negative.
Okay, that's the second step in factoring. Figure out what the signs are. Now we know that we need factors of 4 that add to the number 5. Well, that's 4 and 1. Okay, so where are my vertical asymptotes?
+1, +4.
It's always the first thing I want to do is draw the vertical asymptotes. What's my horizontal asymptote on number 30?
Is it 2?
Uh-huh. So, again, I have a grid for a hyperbolic function. And I know approximately what the hyperbolic function might look like, but I don't know exactly. I don't know whether it crosses the horizontal asymptote or not. And I don't know, I'm suspecting it starts like that. Well, give me a point to see where we're going to start it.
So 4.
4 is right on the asymptote.
Wait, no.
You pick x equal 4, you're going to be dividing by 0. You won't be able to figure it out.
So 5.
Okay? What is y when x is 5? In other words, what is y of 5? 50 plus 15 plus 1 divided by 25 minus 25 plus 4. That's a pretty big positive number. It's 66 over 4. That puts clearly in that quadrant right there. You with me?
Yeah.
Okay. Now, next part, let's check and see what's going on the left. We suspect it's going to be down here, but we're not positive. What's a good value to plug in for x to see? It's the easiest arithmetic.
0.
What is y when x is 0?
1/4.
So when x is 0, y is right there. That spots that quadrant and gives me a y-intercept. Now the only thing I don't know is whether it crosses this horizontal asymptote in the middle. In other words, I suspect that it's like this, but like I said, it could always, if it doesn't cross this, it might end up looking something like that. Well, how do I determine whether it crosses this horizontal asymptote?
Don't you take the put the numerator so it has to equal, or the numerator?
What would y have to be equal to if it crossed this horizontal asymptote?
2.
All right, so let's try to solve this equation. In other words, if this equation has a solution, then it does cross that asymptote, and I know exactly what it's going to look like. So, what's the first step in solving this equation?
Don't you move the denominator over the other
You
side?
always want to get rid of denominators. denominators. When you're solving equations, that's almost always the first step. Get rid of your denominators. So if I multiply both sides by this, I will get 2x squared minus 10x plus 8 on the left. And that's going to be equal to 2x squared plus 3x plus 1 on the right. Well, notice the 2x squareds I can cancel immediately. If I move the 10x to the right, I get 13x on the right. If I move this 1 to the left, I get 7. So indeed, when x is equal to 7 over 13, we're going to be crossing this horizontal asymptote. Well, that's right about there.
All right.
Ooh.
That doesn't make sense.
No, it doesn't. That's outside of my... All right. So, here's the other rule. Graphs can never, ever cross vertical asymptotes. They can cross horizontal asymptotes, and they can cross oblique asymptotes. Okay? So, this only gave me one solution, where it crossed this horizontal asymptote. Well, that means that it's crossing it from this part down here. In other words, what this thing's going to look like is this.
Okay.
Now, what's going on in the middle? It clearly is never crossing that, because it only crossed that at that point right there. So it's not going straight up. It almost certainly is going to be doing something like that. I don't know. We'd have to do more research. I'd want to find out where it crosses the x-axis and how many times.
Yeah, if it's only once, it's up above that.
Well, that's
So
a good question.
it's a unit.
That's a very good question. I'd have to do some more research on this. In other words, if it only once, what's it going to do? I'm not sure.
Can it be above?
It could be above. I'm not really sure, Mitch. I would have to do a little investigation here. I know we're out of time, but I would first of all want to know where my x-intercepts are. I would secondly want to know what it is when x is 2 and 3. In other words, I would plug those two values in for x, figure out what y is, so I get a couple points. Obviously, any graph can be graphed by plotting points. Plug in x equal 2 and figure out where y is. Plug in x equal 3 and figure out where y is. The only thing that I'm relatively certain is it does not cross that line in between those asymptotes. Not unless I made a mistake with my math. I don't think I did. No, x equals 7/13 is the only place where that thing crosses that horizontal asymptote. And that has to be to the left of this vertical asymptote. And yet, part of me tells me that I don't know what the middle could look like, because I don't think it can look like this, because then I'm going down to negative infinity and I'm coming up from negative infinity. Just before you hang up, let me graph this. Let's just take a look what it looks like. Because I'm a little curious myself. Okay, I'm going to need parentheses. 2x squared plus 3x plus 1 divided by x squared minus 5x plus 4. Let's see what this puppy looks like. I put it in right? I did.
What the heck?
this is what it's doing down below.
Okay.
And we can't see it on this big scale. Notice that the only difference between these two plots is this is a smaller scale, this is a much bigger scale. If you put kind of the two of them together, you can see that what's going on in between these vertical asymptotes is this thing right here. Okay, so it does look like the picture I've drawn. I think.
Yep.
I'm not quite sure what's going on up here. This doesn't look like the same graph as this. Does it to you?
No.
No, it doesn't. I don't know what's going on there. It's something you might want to play with on your own.
Yeah.
Figuring out what that looks like in between. Because something doesn't make sense here. And I'm not quite sure what it is. I know we need to leave. So, all right. I will talk to you next Tuesday, right?
Yeah.
All right. Have a good one, Mitch.
Thanks.
Bye-bye.